You're about to embark on a journey through the fascinating world of quantum physics and space-time theories. Imagine a universe where two particles, no matter how far apart they are, can instantly affect each other. Sounds like a science fiction plot, right? But it's not. This is the bewildering world of quantum entanglement. In this realm, a pair of particles can be entangled in such a way that the state of one particle immediately influences the state of the other, no matter the distance between them. This spooky action at a distance, as Einstein once called it, challenges our everyday understanding of the world. Now, let's take a leap from the quantum world to the cosmos. Imagine a shortcut through the universe, a tunnel through space-time connecting two distant points like an interstellar superhighway. This is the concept of a wormhole, a theoretical passage through space-time that could create shortcuts for long journeys across the universe. Combining these two mind-bending concepts may sound like an ambitious mashup of a quantum physics lecture and a space opera. But could there be a connection between quantum entanglement and wormholes? Could these theories together open up possibilities for faster-than-light travel? A concept currently confined to the pages of science fiction novels and the frames of blockbuster movies. As we explore these intriguing theories, remember, we are venturing into largely uncharted territories of physics. The concepts of quantum entanglement and wormholes push the boundaries of our understanding, raising more questions than answers. But isn't that the beauty of science? The constant quest for knowledge, the thrill of the unknown, the audacity to ask, what if? So, fasten your seatbelts and prepare for a journey at the frontier of scientific thought. We'll be navigating through the microscopic world of quantum particles, traversing the vast expanses of the universe, and diving into the intriguing interplay between quantum entanglement and wormholes. Join us as we delve deeper into the mysterious realms of quantum entanglement and wormholes. Imagine two particles so intimately connected that the state of one instantaneously affects the other, no matter the distance. Welcome to the world of quantum entanglement. In the realm of quantum physics, there is a phenomenon that defies our everyday understanding of the world. It's called quantum entanglement, a strange and counterintuitive concept that has intrigued and puzzled scientists for decades. Quantum entanglement is a peculiar kind of relationship that can develop between quantum particles. Once particles become entangled, they remain connected, no matter how far apart they are. Change the state of one, and the other changes instantly. This interaction happens faster than the speed of light, something that challenges our understanding of the universe. So, how do particles become entangled? Well, they need to interact physically in some way. For example, if two particles are created at the same time and place, they can become entangled. This entanglement continues even when the particles are separated, even if they are on opposite ends of the universe. Now let's talk about the Einstein-Podolsky-Rosen paradox, better known as the EPR paradox. This thought experiment was proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. They argued that quantum mechanics, with its spooky entanglement, was incomplete. They didn't believe that an action on one particle could instantly affect another particle far away. The EPR paradox sparked a great deal of debate and brought quantum entanglement into the limelight. Over the years, however, experiments have repeatedly confirmed that quantum entanglement is real and that it does indeed allow for this kind of instant connection. Today, quantum entanglement is a cornerstone of quantum mechanics and a key tool in emerging technologies like quantum computing and quantum cryptography. Quantum entanglement, a phenomenon so strange, Einstein himself called it spooky action at a distance. Yet it's this very spookiness that makes it one of the most fascinating aspects of quantum physics and holds the promise of revolutionizing our understanding of the universe. Could quantum entanglement hold the key to instantaneous information transfer? This is the tantalizing question that has been at the heart of numerous scientific explorations. The unique correlations that result from the entanglement of particles suggest that the state of one particle directly affects the state of its entangled partner, no matter the distance separating them. This phenomenon, often referred to as spooky action at a distance, has been one of the most intriguing aspects of quantum mechanics since its inception. Theoretically, this could mean that information could be transferred instantaneously between entangled particles, bypassing the speed of light limit set by Einstein's theory of relativity. Imagine a universe where information can be teleported across the vastness of space in the blink of an eye. This is the power of quantum entanglement. But before we get too excited, it's important to note that there are significant challenges and limitations to harnessing the power of quantum entanglement for practical applications. For starters, entangled particles are incredibly delicate. Any interaction with the environment can cause the entanglement to break, a process known as decoherence. This makes maintaining and manipulating entangled particles extremely difficult. Moreover, while quantum entanglement allows for the instantaneous correlation of particle states, it doesn't allow for the transfer of classical information. To put it simply, even if you could use entangled particles to transmit information, you'd still need a classical signal to read that information, which can't travel faster than light. Finally, the creation of entangled particles itself is a complex process that requires highly controlled environments and sophisticated technologies. As of now, we are only able to create entangled particles on a very small scale, far from the grand visions of instantaneous interstellar communication. While the potential is tantalizing, exploiting quantum entanglement in practice remains a formidable challenge. But as we continue to delve deeper into the quantum realm, who knows what possibilities we might unravel? After all, the journey of 1,000 miles begins with a single, albeit entangled, step. From science fiction to theoretical physics, wormholes have captured our collective imagination. These curious constructs of space-time are not just the stuff of Star Trek and Interstellar. They have a firm basis in the world of theoretical physics, particularly within the framework of Einstein's theory of general relativity. At their most basic, wormholes are theorized to be like shortcuts through space-time. Imagine you're on one side of a piece of paper and you want to get to the other side. The most obvious route is to travel across the flat surface. But what if you could fold the paper so the 2 points meet? The distance between them is now effectively reduced to zero. That's a very simplified analogy of a wormhole. Wormholes are predicted by the equations of general relativity, which describe how massive objects like stars and galaxies curve space-time around them. Just as a bowling ball placed on a trampoline warps the surface, so too does a star warp the space-time around it. Now, if space-time can be curved, then, theoretically, it could also be twisted and contorted to form a tunnel-like pathway. This pathway, or wormhole, could connect two distant points in the universe, creating a shortcut through space-time. But it's not as easy as folding a piece of paper. The creation and stabilization of a wormhole would require a type of matter with negative energy density, a form of matter that is yet to be discovered. Moreover, any wormhole that does form is predicted to be highly unstable, collapsing in an infinitesimally small amount of time. Despite these challenges, the study of wormholes has provided valuable insight into the nature of space-time itself. It's also led to exciting theoretical possibilities, such as using wormholes for time travel or faster-than-light travel, concepts we'll delve into in the next scene. Wormholes, the universe's potential shortcuts, remain one of the most captivating mysteries of our cosmos. As we continue our journey into the world of quantum entanglement and wormholes, let's keep our minds open to the endless possibilities that await. Could quantum entanglement and wormholes be intertwined in ways we are just beginning to understand? In the intricate world of quantum physics, the phenomena of entanglement and wormholes seem to be peculiarly linked. This connection is not merely a far-fetched idea, but a scientific hypothesis that has been gaining momentum in recent years. It all started when physicist Juan Maldacena proposed an audacious theory, suggesting that a pair of entangled quarks could give rise to a wormhole. This theory, known as the ER=EPR conjecture, hinges on the premise that the entanglement of particles, a phenomenon described by Einstein, Podolsky, and Rosen, is equivalent to the existence of a wormhole, a concept first postulated by Einstein and Rosen. According to this conjecture, the mysterious correlations observed between entangled particles could be explained by a wormhole, or an Einstein-Rosen bridge connecting them. This wormhole acts as a shortcut through space-time, allowing information to be transmitted instantaneously. irrespective of the distance separating the particles. Intriguingly, this theory seems to reconcile the two seemingly incompatible pillars of modern physics, quantum mechanics and general relativity. On one hand, quantum entanglement, a cornerstone of quantum mechanics, suggests the possibility of instantaneous information transfer. On the other hand, general relativity, which describes the fundamental structure of space-time, prohibits faster-than-light communication. The ER=EPR conjecture proposes a middle ground, where these two principles can coexist. However, it's important to note that this theory is highly speculative and remains a topic of intense debate among physicists. There are many open questions and challenges to be addressed. For example, how can we create and control wormholes? How would they behave in the quantum realm? These are just a few of the many questions that need to be answered. The interplay between quantum entanglement and wormholes continues to intrigue scientists and fuel exciting research. Let's continue this journey together as we explore the fascinating possibilities that lie at the intersection of these two enigmatic phenomena. The combination of quantum entanglement and wormholes might just open the door to faster-than-light travel. The idea might sound like it's ripped straight from a science fiction novel, but it's a concept that has been seriously considered within the scientific community. Imagine for a moment that we have two entangled particles. No matter the distance between them, a change in one instantaneously influences the other. Now, let's add wormholes into the mix. These theoretical tunnels through space-time could potentially allow for immediate travel between 2 points, no matter how far apart they might be. If we could somehow link these entangled particles with a wormhole, we could potentially have a shortcut through the universe, enabling faster-than-light travel. Of course, this is purely theoretical. The existence of wormholes is yet to be proven, and even if they do exist, there are numerous hurdles to overcome. For instance, stabilizing a wormhole long enough for anything to pass through is a significant challenge. Not to mention, we're still figuring out the intricacies of quantum entanglement and how we might harness it for practical purposes. The scientific community is divided over these possibilities. Some believe that such travel could be possible, while others argue that the laws of physics as we understand them would prevent it. These debates are crucial in driving the scientific process forward, challenging our understanding of the universe and pushing us to explore uncharted territories. Despite these challenges and debates, the prospect of faster-than-light travel continues to captivate scientists and dreamers alike. The idea of hopping from one point in the universe to another in an instant is undeniably appealing. Whether we'll ever achieve such a feat remains to be seen. But one thing is for sure, the quest for understanding these complex concepts will undoubtedly continue to fuel our curiosity and drive us to explore the farthest reaches of the universe. While faster-than-light travel remains firmly in the realm of theory, it's a tantalizing prospect that continues to inspire scientists and dreamers alike. Harnessing the power of quantum entanglement and wormholes is no small feat. The journey to this ambitious destination is strewn with substantial challenges. First, there's the monumental task of generating and maintaining quantum entanglement on a macroscopic scale. Today's technology allows us to entangle particles, yet scaling up to larger objects, say a spacecraft, is a mountain yet to be climbed. Next, there's the puzzle of creating a wormhole, let alone stabilizing one. Theoretical physics suggests the possibility, but solid proof or a practical method to achieve this remain elusive. Again, we're talking about a leap from the microscopic world to the macroscopic one. It's akin to jumping from a puddle to an ocean. Then there's the issue of traversing these wormholes. Even if we manage to create a stable wormhole, we must ensure safe passage, high-energy environments, gravitational tidal forces, or an unexpected collapse. These are but a few of the perils that may await. And of course, there's the speed of light. Einstein's theory of relativity asserts that nothing can travel faster than light. So if we're talking about faster-than-light travel, we're essentially talking about breaking the cosmic speed limit. That's not something to take lightly, no pun intended. Beyond these technical hurdles, there are ethical and safety considerations to ponder. What are the consequences of tampering with the fundamental fabric of our universe? What safety measures should we put in place to protect explorers and indeed all of existence? In essence, we're not just dealing with the laws of physics here. We're dealing with the laws of responsibility, accountability, and caution as well. We're grappling with questions that have the potential to redefine our understanding of reality and our place within it. The road to realizing these advanced technologies is fraught with challenges, yet the potential rewards are too great to ignore. As we conclude our journey, let's take a moment to recap the fascinating concepts we've explored today. We embarked on a voyage through the enigmatic world of quantum entanglement, diving into the mysterious phenomenon where particles, no matter how far apart, seem to influence each other instantaneously. We then ventured into the theoretical realm of wormholes, those intriguing shortcuts through space-time that could possibly connect distant points in our universe in the blink of an eye. In our pursuit of knowledge, we dared to connect these two seemingly disparate concepts, exploring theories that point towards a tantalizing possibility, faster than light travel. Yes, it sounds like the stuff of science fiction, but who's to say what the future holds? As we navigate the challenges and debates within the scientific community, let's remember the power of curiosity and the thrill of the unknown. Continue exploring, continue questioning, and who knows, you might just stumble upon the next big breakthrough in our understanding of the universe.